So here is what we covered last time. So in the last class, we discussed the problem of electromagnetic radiation in a box, and we said that this was the underlying, uh, you can say that it's a model for an ideal black body, because free space is an ideal black body, and free space containing electromagnetic radiation in a finite volume is what we discussed. And what we did was we started counting the density of states. First, we established that this system behaves like a collection of harmonic oscillators. And then once we know that there are a large number of uncoupled harmonic oscillators, and knowing that the principle of equipartition of energy ensures that irrespective of the frequency of each oscillator, what you have is an equipartition of energy of kBt per oscillator. The problem reduces to a mere counting of how many oscillators exist in a particular uh, frequency range or something like that. So in that regard, we came up with an expression for the density of states. Okay, so the density of, sorry, the density of states in frequency and we were working with angular frequency omega. This is the number of states. This is defined as the number of states or modes with frequency omega. Okay, so this we called, I think, I don't remember the symbol that we used. Let me quickly look it up in the last class. So the density of states that the symbol that we used was, well, yeah, actually did not use any symbol, it looks like. Fine. All right, we did not use any symbol. That makes it easy. So let me call it Z of omega. Okay, Z of omega. So Z of omega, we found the expression to be, it's proportional to the volume, of course. Okay, so it's proportional to the volume of the cubical box. So we considered a cubical box made of perfect conductor on all sides, on all faces. So we had V by C cubed omega squared d omega by pi squared. Now this was the density of states. Okay, sorry, this is Z of omega d omega is given by this. This is the number of states in a frequency range from omega to omega plus d omega. Now, if you want to write it in terms of, if you write nu is 2 pi, sorry, omega is 2 pi nu, where nu is the frequency, normal frequency and not angular frequency, we can write Z of nu d nu to be V by C cubed omega squared can be written as 4 pi squared d nu times 2 pi nu squared d nu divided by pi squared. So that will give us 8 pi by C cubed 4 pi squared, sorry, 8 pi V by C cubed nu squared d nu. Okay, so this is the density of states. Now, if we know the average energy epsilon nu per mode of frequency nu, then the energy contained in the spectrum, in the EM spectrum, between nu and nu plus d nu is given by epsilon nu times z of nu d nu. That will just be 8 pi v by c cubed nu squared d nu times epsilon nu. Right? All we did was multiply the frequency, multiply the average energy per frequency mode E nu. And if we want the energy density would be E nu z of nu d nu by V per unit volume. This is energy per unit volume, and that would just be 8 pi by c cube nu squared d nu epsilon nu. Okay, this is the energy density. Okay, so this we'll call it u of nu d nu, where u of nu is the energy density per unit frequency, per unit frequency, per unit bandwidth. Actually, it's not called per unit frequency because d nu is the bandwidth, so per unit bandwidth. All right, so this is the energy density per unit bandwidth of black body radiation, and it is this epsilon nu that we now need to figure out. But thanks to equipartition, so classically equipartition theorem, which we have discussed extensively, says that epsilon mu is nothing but kBt. Therefore, u of nu d nu for a black body classically comes out to be 8 pi by c cubed nu squared d nu times kBt. Now, to get the energy in all the frequency range of the black body, we have to integrate from 0 to infinity u of nu d nu, and that is infinite, and this is absurd. Okay, because this factor blows up, and this is what the Rayleigh-Jeans law for the black body radiation predicts. Now, while this was the first theoretical attempt at predicting the black body radiation, people had already measured the spectral density of black body radiation as a function of frequency, and they found a plot which looked something like this. So the Rayleigh-Jeans prediction actually worked in this direction, in this range. The RJ prediction worked in the low frequency range, but in the high frequency range, it completely failed. So people started figuring out what was the reason, and this itself, this failure of the classical model and thereby the equipartition energy to predict the full black body spectrum itself was enough signature, or was an enough warning to suggest that classical physics was inadequate. This inability to predict, inability of the classical model to predict the full black body spectrum is an indication that classical physics is inadequate. So then people started looking at what might be alternatives. Now,
Sir,
yeah.
So earlier we had said that the modes are discrete, have discrete frequencies, but here we are talking about bandwidth. So isn't that contradictory?
It's not contradictory. We said that discrete frequencies are when the length of the box is, say, small. But as you increase the length of the box, these frequencies can be treated as a continuous variable. And therefore, that is the whole approximation under which we can even count the density of states, right? Otherwise, every frequency has only one mode or two modes.
Yes, sir, got it.
So the notion of a density of states exists only in the case of a continuous or a quasi-continuous set of modes. And usually the approximation is that the volume that you consider is large enough to make these modes dense in the frequency space. All right. So classical physics is inadequate. So the first attempt to even the first attempt to improve this situation was made by Wien. Okay, Robert Wien. He made some very important observations. So before we understand what Wien came up with to address this issue, so just to give you a sneak preview of what Wien did. So if you see, this is U of nu and this is nu. The black body spectrum looks something like this with a tail, long tail, and the Rayleigh-Jeans prediction fit the curve in the lower frequency range. What Wien did was he fit the curve in the higher frequency range. And what Planck did was he came up with an interpolation formula which fit everything in between. That's what we are heading towards. Okay. So before we understand what Wien did, we need to look at a very simple problem. So people may have this feeling that, oh, all of classical physics was discovered by the 1800s and quantum physics, all the work in the entire community happened only in the direction of quantum physics in the first half of the 20th century. But that's not true. In fact, a very simple, extremely simple problem in classical physics was the center of attention in the first decade of the 1900s, that is the 20th century. And this problem gave some of the most important insights. Okay, so we are kind of going back in history a little, or rather we are kind of jumbling up history a bit, because Rayleigh-Jeans law is from the late 1800s. Max Planck's discovery of the full black body, the formula that fit the entire black body spectrum, is from 1900. But let us now go back and look at this simple classical problem and try to understand how that has some insights to the black body radiation problem. And knowingly or unknowingly, this is exactly what Wien did. So let's consider a pendulum. We all know a simple pendulum, and we know that a simple pendulum for small angles. So let's consider, and the problem is called an adiabatically perturbed pendulum. Why adiabatic, etc., we will see in a minute. But let us consider a simple pendulum to begin with. For small oscillations, the pendulum has, let's say it has a length L. Theta double dot plus G by L theta equal to 0. And for finite oscillations, the pendulum will have an equation. This is a nonlinear equation and this is a linear equation. This is linear and this is nonlinear. The bottom equation can be solved, but it's not going to be you can't get a simple closed form solution, and it is also not a simple harmonic oscillator in the sense that the frequency will depend on the amplitude. Okay. Now, the potential energy, the total energy of this pendulum can be written as half ml squared theta dot squared, right? That is the kinetic energy of the pendulum plus mgl to 1 minus cos theta, right? For example, if I take the reference point when the pendulum is oscillating like this, the reference point at this lowest position, if I take that to be the zero of the potential energy, then this will be the potential. Now for theta small, as theta goes to zero, the approximate form of the energy can be half ml squared theta dot squared plus mgl 1 minus cos theta is theta squared by 2. Okay, cos theta is 1 minus theta squared by 2 plus so on and so forth. So 1 minus cos theta will be roughly theta squared by 2 for small theta. All this is very familiar stuff. And if you solve this equation, the solution for this equation will be theta dot plus g by L theta will be theta dot plus 2 pi nu. Nu is the frequency of the pendulum. 2 pi nu theta will be 0. Squared. 2 pi nu squared theta will be 0. And the general solution for this will be written in terms of minus some phi. Okay, this will be the oscillation of the pendulum. So far, any questions? Any questions so far? All we have done was to compute the average energy, the energy and the solution of the pendulum itself for small angles. Now consider the slightly different problem where we have a pendulum which is undergoing small oscillations, but we are gradually pulling it up, gradually, very, very slowly. Now this rate of movement of the pendulum upwards, so we are pulling the pendulum up. This is done almost quasi-statically, and the rate at which we are pulling, the time scales are much, much, much longer than the oscillation time period of the pendulum. Okay? So this is the idea. Now, what is the tension in the pendulum? So if you look at any particular angle theta, okay, if the pendulum is some angle theta, you have mg acting this way, so mg cosine theta acts this way, and then you have the centripetal acceleration. So the tension will essentially provide both. So it will provide mg cos theta plus ml theta dot squared. This will be the tension in the string. All right. And for small theta, for small theta, all this analysis is happening for small theta. So we'll write every expression mg 1 minus theta squared by 2 plus ml theta dot squared. All right. Now let us do a simple analysis. So what is the tension as a function of time? For that, all we need to do is substitute the solution for theta and theta dot as a function of time into this equation. The tension as a function of time for this oscillating pendulum will be mg 1 minus the theta is a cos 2 pi nu t minus phi. Let us forget the phi part. Okay, let us just make this phi 0 for simplicity. So it will be a squared cos squared 2 pi nu t. Okay, that will be the theta squared divided by 2 plus ml theta dot squared will be 2 pi nu a, okay, squared, and there is no half here. Yeah, there is no half here. Sine squared theta, sine squared 2 pi nu t. This would be the derivative, the time derivative. So t of t can be written as approximately, and since the rate of, so let's now write it, mg a squared yeah, and we will also use 2 pi nu is g by L. Here if we substitute 2 pi nu equal to g by L, 2 pi nu squared will be, sorry, 2 pi nu squared will be g by L. That will give us an mg a squared here in the second term also. And what we get is half cosine squared 2 pi nu t minus sine squared 2 pi nu t. I want you all to kind of mentally do this calculation. What I am doing is 2 pi nu is square root of g by L for a pendulum. And I am substituting that formula here, and g by L, the denominator L and this L will cancel out, and I get an mg a squared sine squared 2 pi nu t, and I take that common with the first term and I get a half here and like this. Okay, so the average tension, if you now compute the average tension over one period of oscillation, is T of t. So I'm not going to say T of t anymore because that is now an average quantity. So the average value of t will be mg minus mg a squared times cosine squared will give you a half and sine squared will give you another half. So you get 1/4 minus half. So this will give you mg plus mg a squared by 4. This is the average tension. Okay. Now, the first term is very obvious. It came from the force of gravity. But what is the second term? This is the term, since we are, we are studying a pendulum, but this term is something that depends on the amplitude of the oscillation, and it is in other context identified as the radiation pressure term. Okay. So the average tension is now a sum of two terms. One is due to gravity, and obviously if the angle of oscillation is symmetrical about the vertical, then the tension will be on average just the mg, which is fair enough. And then you have an additional term which is due to the amplitude squared, and that term is always positive, and it's called the radiation pressure. Okay. Now, if you move this pendulum, if the length of the pendulum changes by delta L, okay, then the average work done on the system by the agent who is pulling that pendulum up will be basically the if you see this diagram here, since this is a massless pulley, this tension here is basically the tension here in this pendulum, right, in this string. So the work is being done against this tension. So the work done by the agent, external agent, will be the average tension times delta L, and that would just be mg delta L plus mg a squared by 4 delta L. Okay, so far everything is quite straightforward. But then what is this first term here? This first term is basically lifting the entire pendulum up by a distance delta L. But we are interested in the oscillation energy of the pendulum and not so much at what height the whole pendulum is. Okay, so this is purely work against gravity. And this second term is the work done on the oscillation of the pendulum. Okay, and we ignore this. We ignore this first term because that's not what we are interested in. So if we just consider the work done on the oscillational part of the energy of the pendulum, then that would just be mg a squared by 4 delta L. Okay, now this is nothing but this is the net change in the oscillation energy of the pendulum, because that's the work done. Here is where the name adiabatic comes into play. So if you think of the first law of thermodynamics, you have delta Q equal to delta E plus delta W, where delta E is the change in the internal energy and delta W is the work done. Okay. Now, work done by the system. What we are saying here is delta Q, if you put delta Q equal to 0, which is the idea of an adiabatic process, then delta W will be minus delta E. That's precisely like this equation. The sign convention, of course, here delta W means the work done by the system. Here we are computing the work done on the system, and that would be the increase in the oscillational energy, basically. So so delta E, so the change in the oscillation energy of the system will now be equal to the work done on the system, which is the negative of the work done by the system. So which is basically mg a squared by 4 delta L. This is the change in the oscillational energy. So in this sense, it's an adiabatic process. There is no heating involved. The work done will be the change in the energy. Now, if you consider the total energy that we wrote down, ml squared theta dot squared by 2 plus mg L theta squared by 2. For the oscillation, this is nothing but half mg a squared L, right? Because if you just put in theta dot squared here and theta squared from the solution, this will be half mg a squared L. Therefore, if you now compute delta E by delta E by E, the ratio, that is nothing but half delta L by L, because mg a squared will just cancel. Here is a 4, here is a 2, so you get half delta L by L. Let's call this equation A. What we have computed is the relative change. Those of you who have done any error analysis will identify that this is basically the fractional change in the energy due to a fractional change in the length of the pendulum. Okay, and we have nu is 1 by 2 pi square root of g by L. This is the frequency. If you now compute by similar, interpretation, the fractional change in the frequency as a function of the L, you get half delta L by L again. Now, therefore, delta L by E equal to delta nu by nu for a pendulum. And we saw that all oscillators are basically one and the same. So therefore, delta E by E equal to delta nu by nu for any oscillator. And what does this equation mean? Delta E by delta nu is equal to E by nu. Okay. If you see the left side, that's the derivative. This is like dE by d nu. Okay. Whereas this here is E by nu. When is the derivative equal to the ratio of the coordinate by the abscissa for a straight line? Right? For example, if you have a straight line, then dE by d nu will be this. This is E, this is nu. Whereas that is exactly equal to E by nu. This is E and this is nu. This here is dE and this is d nu. dE by d nu equal to E by nu. That means E by nu is a constant. So what did we just show? Using very simple analysis from what we know from high school and using nothing more, we showed that for any oscillator undergoing an adiabatic or slow change in the surroundings or parameters of the problem, E by nu is a constant. So this is called adiabatic invariance. Okay, this is called adiabatic invariance. Now this problem led to people discovering this notion of adiabatic invariance. Okay, and then people went back and looked at the classical mechanical theory, and here is what they discovered. Okay, so we looked at a particular quantity which is adiabatically invariant for an oscillator, which is E by nu. In general, for any conservative bounded system. Now, what do we mean by conservative bounded system? A system that has its positions and momenta. So every system is mechanical system, bounded mechanical system, that is. For any conservative bounded and for any conservative bounded mechanical system, the coordinates and momenta are finite. Okay. For example, an oscillator is a bounded system. Okay. A planetary system, for example, is a bounded system. A two-body gravitational attraction is a bounded system because you have, I'm not saying all orbits are bounded. For example, you can have asteroids and comets also described by the same potential. But if you have an initial condition which sets the planet in motion around the star, that is a bounded orbit and it's a periodic orbit. So it keeps repeating itself, right? So such systems are called bounded systems. And for all such bounded systems, since every mechanical system, let us say, has x1 to x3n and p1 to p3n, these are the 6n dimensional phase space. What people figured out was that integral over a closed path of this particular quantity pi dqi. Okay, if you take the momentum pi and you integrate it along a closed contour in the phase space. This is an adiabatic invariant. Okay. You can already see, those of you who are familiar with a little modern physics will already see that you are kind of looking at an earlier version of the Bohr's quantization rule. Of course, we are not saying anything quantum here. This is purely classical physics. So what people figured out is that integral pi dqi is an adiabatic invariant. Every such pairs. So if they, yeah.
Figured out, you mean they proved that this is the case?
They proved, yeah, they mathematically proved it. Is that clear?
Yes.
Yeah, so integral pi dqi is an adiabatic invariant. And now let us use this analysis. So the energy for an oscillator is basically p squared by 2m plus q squared half k q squared, right? Now this is basically p squared by 2m plus q squared by 2 by k. Okay, and if you take a particular contour of energy E, you get p squared by 2me plus q squared by 2e by k equal to 1. This basically is the equation of an ellipse, right? This is the equation of an ellipse. Any doubts there? Now, if you consider for a pendulum, let us now, since we just looked at a pendulum, let us look at Q for the pendulum is basically the theta, and P is P, which is the momentum, and we can, for the pendulum, we can write P theta squared, sorry, P squared. For the pendulum, it won't be P squared by 2m, but it will be P squared by 2m L squared, because that's an angular momentum we are talking about, plus theta squared half theta squared mgl will be E. Okay, so therefore for a pendulum where P is actually the angular momentum, okay, just remember that it's an angular momentum and not a linear momentum. So P squared by 2m L squared E, okay, plus theta squared by 2 by 2e by mgl will be 1. Now if you consider integral p d theta, okay, going over a full trajectory, that is nothing but the area under this ellipse, right? And we know that this is the area under the ellipse. And we know that if x squared by a squared plus y squared by b squared equal to 1 is the ellipse, area is given by pi times a times b. This is a standard result from geometry. So let us now compute integral p d theta for the pendulum, which will just be pi times a. A will be square root of 2m L squared E times square root of 2e by mgl, and that will be 2 pi, I take the 2 out, square root of L by g times E. But you know that the frequency nu of a pendulum is nothing but 1 by 2 pi square root of g by L. So whatever factor is here, it's basically E by nu. Therefore, integral p d theta for a pendulum is nothing but E by nu. In general, for an oscillator, by the same analysis, integral p dq will be E by nu. So E by nu is an adiabatic invariant, and we derived this earlier using simple Newton's laws and a very nice calculation. But from a classical mechanics perspective, this is a more general phenomenon, and every quantity which is of this form integral p dq, where q is any coordinate, it can be an angle, it can be a spatial coordinate like the Cartesian coordinates, it doesn't matter. If it's an angle, the corresponding momentum will be an angular momentum. If it's a linear coordinate, then the corresponding momentum will be a linear coordinate, linear momentum, but it doesn't matter. Whatever it is, integral p dq will always be an adiabatic invariant, and for an oscillator in particular, this quantity integral p dq, because an oscillator has only one momentum and one coordinate. In the case of a pendulum, it is theta and the corresponding angular momentum. In the case of a spring mass system, it is the linear displacement x and the corresponding linear momentum. Whatever may be this situation, there is one coordinate and one momentum for every oscillator. So for an oscillator, this is the adiabatic invariant. But you can in principle think of a system of coupled oscillators with oscillators in different directions. Then for each direction, that is each normal mode, for each normal mode, there will be an adiabatic invariant like this. Okay. So this is a very, very important result in the history of physics. And so for a collection of oscillators, of coupled oscillators, we can compute the normal modes. And once we have the normal modes, then each normal mode is like a single oscillator, and integral p dq will be E by nu for it. And that's a constant. That is an adiabatic invariant. Now, why is this result important? What insights did this result have for the black body radiation problem? So it turns out that Wien applied this principle to the adiabatic, to the black body radiation, and this is what he achieved. So Wien's approach to the black body radiation problem. Okay. Now, we know that delta E, so the black body radiation is a collection of oscillators, electromagnetic oscillators, and let us say we consider the mode N. Okay. Then the mode N has a frequency nu n, let us say. Then according to the just proven theorem of adiabatic invariance, this quantity, this is the equation, and this has to be equal to okay. Now this I just want to Yeah, there is a factor of 2 in the denominator. Sorry.
So why is it minus del L by 2L?
Oh, because as the length increases, the energy of oscillation goes down, right? That's why.
Okay, sir.
Yeah. Now, we did the particular analysis earlier for pendulum, but if you do the same analysis for an electromagnetic oscillator, this is what you will get. Remember that for a pendulum, we had square root of G by L, because of which there is a factor 2 that we got here. But for an electromagnetic oscillator, you won't get that. I'm not going to do exactly that analysis, but I'm going to just state the result, saying that for an EM oscillator mode, it's not very hard to see, but this is now, if you consider a cubical volume, and let us say you are changing the volume adiabatically, this is like changing the length of the oscillator, but in 3 directions, then delta En by En should be equal to minus 1 by 3. This delta L by L can actually be written as delta V by V, because V is L cubed. So you get delta V by V will be minus 1/3 of delta L by L. Sorry, it's 3 times delta L by L. Therefore, delta L by L is 1/3 of delta V by V. Okay, so this is something that now consider a tiny change in the volume of a cubical cavity which contains radiation in free space inside it. If you do a similar analysis, delta W will be the work done on the electromagnetic modes of this cavity. That would be summation over all n delta En, where delta En is the change in the energy of each oscillatory mode, and that would be minus 1 by 3 summation over n En. If you just take En to the other side, delta V by V. Now, summation over all modes En by V is what this is a discrete summation, but if you take into account the integration over all modes, and by modes I mean over all frequencies, this is what we call the U, that the energy density earlier, right? This is the energy density. I'm not saying U of nu, but this is actually integral U of nu d nu over all frequencies. Let's give this the name U. Without the U of nu, I'll just call it U, which is the energy density in the electromagnetic spectrum per unit volume integrated over all frequencies. Now, what did we get? What we got is delta W, which is the work done on this electromagnetic cavity, is U times minus 1 by 3 times U times delta V. Therefore, delta W by delta V is minus 1 by 3 U. If you now think of this electromagnetic radiation inside as a sort of a gas, minus delta W by delta V is actually the pressure of the gas. This is the radiation pressure. Okay. Therefore, the radiation pressure of an electromagnetic radiation inside a cavity is 1 by 3 of U, where U is the energy density, energy per unit volume. And we are not saying energy per unit volume in a certain frequency range. No, that is U of nu. This is just U, which is the energy density per unit volume. Now, without deriving anything, okay, without deriving anything. The derivation is actually in the notes that I shared last week, in the Gibbs principle notes. Starting from this point, Boltzmann showed that this energy density U, which is the energy density in the electromagnetic spectrum, it is proportional to T to the power of 4. This is basically another version of Stefan's law. Okay. And Stefan's law was experimentally verified. So now what are we really saying here? We are saying that the notion of adiabatic invariance is applicable to the electromagnetic spectrum, and using that we can construct a relation between the radiation pressure and the energy density of the electromagnetic modes inside a cavity. And starting from this energy density and pressure relation, treating this as a thermodynamic system, Boltzmann constructed a thermodynamic cycle. Okay, and the cycle is actually like this. He constructed a combination of adiabatic compression to isothermal expansion. Okay, sorry, first process is adiabatic compression, then isothermal expansion, then an isothermal compression, to adiabatic expansion. Okay, now using the second law of thermodynamics, if you do this process quasi-statically, there is no change in the entropy. Using this principle, and the derivation is shown in the notes. I want you to go through the derivation. It is a very interesting derivation, but I don't want to spend time in the class going through the derivation. It is quite simple. So I urge you all to go through this. Boltzmann actually showed that this relation for the radiation pressure, which is the 1/3 of the energy density, gives you the correct temperature dependence that is predicted by Stefan's law for an ideal black body, which free space is verily an ideal black body. Okay. Therefore, now what Wien did, all this was evidence that adiabatic invariance is something that you can apply to electromagnetic radiation. So what Wien did was the following. This is called the Wien's displacement law. You have probably heard of the Wien's displacement law in completely different context, but this is the background story of it. What people do when they teach Wien's displacement law is they give you a law without saying the head and tail of what it actually is about. What we are doing here is we are kind of building up the background physics and the background reasoning that led up to the Wien's displacement law. Okay, so here is what Wien's displacement law. So we know E by nu for an oscillator is an adiabatic invariant. And what Wien showed was the following, that nu by T is also an adiabatic invariant. Now this is what we usually call the Wien's displacement law. In fact, if you write nu by T as C by lambda T is a constant, then lambda T is a constant. right? This is what people typically refer to as the Wien's displacement law. So what Wien computed thermodynamically was that, and the derivation is actually not very difficult. It's all again,
Excuse me, sir.
yeah.
Should it be mu max, that is the maximum emission frequency?
Actually, this is true for all frequencies, but nu max is what we usually use.
Sir, how can it be true for all frequencies? Like we can take any frequency and any temperature. So I didn't get.
So we are looking at, no. See, what I mean is the following. For every mode, so what Wien proved was that for every mode of the electromagnetic oscillator, this is true.
Okay, sir.
Yeah, for every mode of the electromagnetic oscillator, this is true. And the frequency, if you consider a very continuous distribution of frequencies, then lambda max corresponds to the mode which is at whatever that corresponding nu. But Wien's analysis shows that nu by T is also an adiabatic invariant for every oscillator, every mode of a collection of oscillators, if you consider a whole bunch of them. Is that clear?
Yes, sir.
Yeah. So now he did something very interesting. What he said is, so for an oscillator as a mechanical system, E by nu is a constant, is adiabatically invariant. For a mechanical system, for any mechanical system, it can be any oscillator. Now for a thermodynamic system, that is an oscillator in equilibrium at temperature T, he showed that nu by T is a constant, is an adiabatic invariant. Okay, now these are two different results. So what Wien conjectured was that these two adiabatic invariants are related to each other by E by nu should be equal to some function of nu by T. Obviously, E by nu and nu by T are dimensionally different, so they cannot be equal exactly. But he said that these are two adiabatic invariants of the same system. So when you are doing an adiabatic process to this electromagnetic oscillations by changing the volume very gradually, it is both a thermodynamic process because you are, the radiation is actually in thermal equilibrium with a certain temperature. So from a thermodynamic perspective, nu by T has to be a constant. From a simple mechanical perspective, where we did not invoke any temperature, E by nu should be a constant. But we are only doing one thermodynamic adiabatic process. We are not really, doing two independent processes here. We are only looking at one system of radiation, which is at the same time a mechanical system as well as a system at thermal equilibrium. So for this system, these two adiabatic invariants have to be related to each other. Therefore, one adiabatic invariant has to be a function of the other. It's a very simple logical argument, in fact. So for mode n of the oscillator, what this means is En will be some nu n times some function, which is nu n by T. So this is what Vn figured out. And if you now consider, this is for each mode n. If you now consider a whole collection of these oscillators like in a finite volume box that we have been discussing, you have to multiply to get the energy density at a particular frequency. You you have to multiply it by the density of states. Therefore, what Wien discovered was that the energy density, which is now a function of T, d nu, has to be 8 pi by c cubed. And earlier we called this epsilon, this is what we meant by epsilon nu earlier. Okay, this is the energy, average energy of each mode. Okay, so that has to now be, so you had nu squared d nu times epsilon nu. This will be 8 pi by c cubed, nu squared d nu times nu, because nu is there, times f of nu by t. Therefore, u of nu t d nu is now 8 pi by c cubed, nu cubed d nu f of nu by t. Now, from our earlier expression, which is this, to this, doesn't seem like a huge progress. But in history, this was a huge step, because at this point, E nu was only a function of temperature, which according to classical physics, this was given by the equipartition theorem of energy. But what Wien figured out using this principle of adiabatic invariance and applying it to the electromagnetic radiation inside a box, that this function E nu is actually a particular, it has a particular shape which is nu times f of nu by t. It turns out that E nu equal to kBt is a special case of it. It turns out that it's a special case of this particular form. So if you choose, if, okay, f of nu by t, okay, if nu times f of nu by t is kBt, we get Rayleigh-Jean's law. Okay, nu times f of nu by t, or f of nu by t equal to kb by nu by t. So therefore, if you call nu by t as x, then this is kb by x. So he immediately realized that the Rayleigh-Jean's expression is a particular case of this general expression, and from adiabatic invariance of oscillators, he said that this functional form has to be true. And then he went about searching for functional forms that fit the black body radiation. So then he came up with, so Wien's fit to the BB radiation. He chose f of x equal to a form of the type k times alpha e to the power of minus alpha x, where alpha is some constant. Okay, and x is nu by t. Okay, this was the form that he chose. That gave us e to the power of nu t d nu, which is k alpha e to the power of minus alpha nu by t 8 pi nu cubed d nu by c cubed. And this particular formula, this fit the high frequency range of the BB spectrum. So now everybody was trying to find the correct fitting function f of x, which fits the entire range, and this was where Max Planck succeeded. Max Planck found the correct f of x. And he found that f of x was some k times alpha by e to the power of alpha x minus 1. And usually he called this k times alpha to be some constant h. Okay. So what Max Planck used was it's some h divided by h nu by kt, where k is Boltzmann's constant. By the way, k here is Boltzmann's constant. I should write it as kb. Okay. This is kb, kb, kb minus 1. So therefore, and this fit the entire range. So what Planck did actually was just a simple fitting exercise. And we are walking in sort of the historical path. And this turned out to be the correct function that fit the entire range of black body radiation. And we are still not calling it Planck's quantum hypothesis. That will be the subject for the next class. So we'll stop here. This is exactly what Planck did. To be very honest, he came up with a fitting function based on what Wien discovered. He said, okay, Wien could fit the higher range and Rayleigh-Jean's expression fits the lower range. Let me now look for an interpolation formula that fits both ranges. And he landed on this formula by trial and error, because this formula has to reduce to kBt in the lower range and has to reduce to a simple exponential in the higher range, an exponential decay in the higher range, and it seemed to work. Then using that, he could fit the entire spectrum. But once he fit it, and once it worked extremely well, it was obvious that the classical picture of electromagnetic radiation satisfying the equipartition theorem of energy had to be thrown out. But then how to reconcile this? What is the underlying physical basis? So this work, this part of the work was carried out by others, and we will, this h here is called Planck's constant. And we will see how this plays a remarkable role in what is to come. And what we will do on Wednesday's class is we will analyze this expression, the energy density of the oscillators, and see how it results not from a continuous spectrum, but from a discrete spectrum. And I'll explain to you what I mean by a discrete spectrum and not a continuous spectrum. Of course, the frequency is continuous, but if you consider energy, you have to treat it now in a discrete fashion. The frequency is still continuous. Remember that the frequency of an oscillator is a classical parameter, which is a continuous variable, but the energy of the oscillator is no longer a continuous variable. And that is this formula. If you stare at it for a couple minutes, you will realize that the difference between this formula and the classical formula that Rayleigh-Jeans used is essentially at the mathematical level simply going back from an integration to a summation. Usually we do the latter. We go from summation, use the Riemann sum and the limit of a Riemann sum is the integral. But here what Planck, without knowing, just to fit the function, he landed on an expression which can be derived only from a summation and not from an integration. And that is what we will take up in Wednesday's class. Any questions?
So when would what would be the time of the midsem?
6th October, 2 p.m.
Yes, sir. I mean, what would be the starting and ending time?
Sorry, meaning?
So as in it's written 2 p.m. onwards. So like the maths mid-sem is from 2:30 to 5. So
So
what
we'll
would be
figure that out. It'll be, let us prepare for a 3-hour exam or a 2-hour exam. I'll let you know. I'll let you know a few days before. That's not a problem.
okay, sir.
Yeah. Any questions on what we discussed today? We discussed a few things which are not very complex, but this is a very important concept which is grossly missing. Adiabatic invariance is not taught in most courses, either on classical mechanics or quantum and modern physics. And this is a very key missing step, because of which a lot of what we do later on in quantum physics, this Bohr's principle and everything seems very, it's like it seems as if they are pulling rabbits out of the hat, but that's not so. There is a very sound physical principle called adiabatic invariance, which they all identified as a very important aspect for oscillators. And it turns out that the adiabatic invariance is not very dominant in classical physics because the timescales of classical systems that we encounter, for example, if you say take a pendulum is usually oscillating at a few, hertz at best. Now, if you want to really change the length of a pendulum adiabatically, you have to do this experiment over several hours, which is not of great interest. But think of an atom. Now, if you even think of an atom as an electron revolving around a nucleus, the time scale on which this electron revolves around the nucleus is going to be, extremely tiny compared to the macroscopic timescales that we conduct measurements in. Now, in that time scale, the environment of an atom is changing, on the scale of the time scales of the atom, the environment is changing gradually, and therefore the atom is actually experiencing an adiabatic process and adjusting to it. And therefore, adiabatic invariants play a huge role in quantum physics. In fact, we will later see that the adiabatic invariants have a direct correspondence with what we now know as quantum numbers. Okay, so let us pause here for today and try to assimilate what I discussed, and we'll continue on Wednesday with what this formula that Planck discovered actually means and how that led to the quantization of energy, which was the first variable to ever be quantized. All right. Okay, if there are no other questions, let's conclude here. We'll meet on Wednesday as usual.